Hello everyone, I am Harshad Goel, third year CA student from IIT Delhi, and today we will discuss the traveling salesman problem. So the plan of today is to first introduce ourselves to the problem, then we'll try to find the optimal solution to the problem, then we'll see the theoretical and practical importance of this problem, and then we'll build our new tool from scratch and then we'll try to improve it. So let's get started with the introduction. So the informal definition of this problem is simply given a list of cities and the distances between each pair of cities. What is the shortest possible route that visits each city exactly once? So let me explain this to you with an illustration. So let's say these nodes are our cities and we need to find a path that visits each city exactly once. So let's say we start from this node over here. So one path could be like this. There. So in graph theoretic terms, this is called a Hamiltonian circuit or Hamiltonian cycle. So now we know what a Hamiltonian cycle is. We can now see the formal definition of this problem, which is given an undirected graph and a cost for each edge of that graph, which can be simply the distance between those two nodes. We need to find a Hamiltonian cycle of minimum total cost. That means the minimum total distance. So here vertices and edges are the analogs of cities and roads. So to put it in a nutshell, we have a complete graph, which means we can go from every node to any node. Then the weights on every edge are positive because these are distances, and the problem can be symmetric or asymmetric. That is, the distance between two nodes I and j may or may not be equal to distance between j and I, but in real problems it will obviously be equal. And also we have the triangular inequality, which means distance between ij is less than equal to distance between ik plus distance kj. And also the distance between any two nodes or cities would be the Euclidean distance that we will consider. So that means we can fly from one city to another, and we have to find the shortest Hamiltonian cycle. So we will first start by finding the optimal solution to this problem. So an exact algorithm would be, we can try all possible permutations of the cities and see which one is cheapest using brute force search. So we order the cities and find all possible permutations, and then we see in which permutation of visiting the cities has the least cost. So we make the search tree. Let's assume that we have only 3 cities for now. So first of all, starting from the root, we can pick any one of the 3 cities, M1, M2, M3, and suppose we chose M1, then we can go either to M2 or to M3. So we have made 2 branches, and then from M2 we can go to M3. So this is how our search tree would look like. I assume that the viewers know what is a tree, but for those who don't, I'll quickly explain that these are called nodes, the cities. These are called branches as labeled, and the bottom nodes are called the leaves. So every node can be called a choice point over here, like which city we choose at what time, and then branch is the alternative we can take from that city, and once we reach the leaf we get a solution. So like one solution would be this M1, M2, M3. First we start with M1, then we go to M2, then we go to M3, and then we come back to M1. This is one solution. So these all are solutions, and we have to find the minimum of them. So we see the problem with this is that the complexity of this algorithm is of the order of n factorial, and we see how this is. Say we order the cities in which we visit them. Since there are n of them, the first city can be picked in n ways, next in n minus 1 ways, and so on till 1. So this gives us n factorial. Now any arrangement, let's say we took arrangement 1, 2 until n. Another permutation would come where this arrangement would just be reversed, but that would form the same cycle. So total we have n factorial by 2 cases. If we do a more rigorous analysis, we can reduce it to n minus 1 factorial over 2, and we can do that by saying that since in a cycle it doesn't matter from where we start, so for the first node we can pick any node, any city, and then the rest n minus 1 we can pick by n minus 1 factorial ways divided by 2 because of the symmetry. So since the complexity is of the order of n factorial, this solution becomes impractical even for only 20 cities, because 20 factorial is a very large number. So there are optimized solutions for this, like branch and bound algorithm, which try to reduce the running time, but they aren't at par. Also, the first attempt to an earlier application of dynamic programming to this problem is the Held-Karp algorithm, which solves the problem in order n squared 2 to the n time, but still it's exponential. Also, it's possible to combine local search with this tree search, and we'll see local search, what local search is in subsequent part of this video. So here what we are trying to conclude is that the order of this solution is exponential, and so it will take a lot of time to run on a computer. Here we try to find a lower bound to the TSP. We claim that a lower bound to the TSP would be a minimum weight spanning tree, and this is fairly obvious, so I don't think it needs any explanation, because a minimum weight spanning tree is just those edges which cover all vertices and such that the total weight summed of the edges is minimum. So that's actually the best we can do. So it's obvious that TSP can not be less than that. So here are some benchmarks for the exact algorithms. Like in 1954 we were able to solve the problem with 49 cities, in 71 with 64, and so on till 2001 we were able to solve the 15,000 cities, but we can see that the solution comes out in 19 years of CPU, which is clearly not feasible. So now we'll look at the theoretical and practical importance of this problem. So the theoretical interest is that because it's a basic NP complete problem. NP complete problems, to put it in simple words, are those which cannot be solved in polynomial time, like we saw the TSP how TSP can be solved in exponential time. The exact solutions take exponential time, and up till now there is no exact solution which runs in polynomial time. So that's why it's a hot topic in theoretical computer science, and there are plus 150 articles in the period of 93 to 2001 about TSP. And also for practical applications, we can say that one of the most obvious applications of this is to the logistics. That is, we need to find good routes for our, let's say, trucks or order pickers, delivery systems, aircrafts, tourists, and some other less obvious applications are scheduling jobs on machines. Like, how should we schedule jobs on a machine so that the total task can be completed in minimum time? And also there are many other applications like controlling satellites, telescopes, microscopes, computing DNA sequences, designing telecommunication networks, and so on. And there are many variants to this problem also. Let's say this is Euclidean traveling salesperson selection problem, asymmetric traveling salesperson problem, symmetric, like we said in the start of this video that we are considering the symmetric TSP, which means that from city 1 to city 2 distance is equal to the distance from city 2 to city 1. In the asymmetric TSP, this is not the case. And these are a lot of variants of TSPs, but we don't need to go into in depth. So, but the good news is that exact methods take exponential time only in the worst case instances, which such instances are actually rare in the real scenario. And also there are many effective heuristics available which quickly find solutions. So now we'll try to build a new tool from scratch. Let's see. So the first heuristic or the first idea that comes to the mind after seeing this problem would be like, let me show you. Let's say this is our graph. So the first idea that comes to the mind is that, okay, we start from a node and we will go to the nearest neighbor of this node, and we see that is this, and we keep going to the nearest neighbor until we visit all the nodes. But as we can see, at this point we need to cover this long distance. So we can get an idea already that this algorithm might have some problem. This might not be accurate to just go to the nearest neighbor, and we'll see another example in the slides. So the nearest neighbor heuristic is start with any node as the beginning of the path, find the node closest to the last node added to the path, and repeat the step 2 until all nodes are contained in the path, then join the first and last nodes. So let's build a path by this heuristic. Again, as we have seen in our example, here also we can see that the problem of the last edge becoming really long comes over here. So the nearest neighbor heuristic is actually a greedy approach, like we go to the nearest neighbor always, and greedy is not necessarily the solution of any problem. We have to always prove that a greedy solution works. In this case it doesn't, and also it's order dependent, like it matters in which order we are traveling and from which node we start. And some neighbors are not so near, like we can see over here. So there are other heuristics also for this, like the nearest insertion heuristic. So what we do in this is that we start with a node I, we find node k such that Cik is minimal and form subtool Iki. Let me show you what this means. Let's say we start from this node over here. Now we'll start forming our two one by one. Let's say now we added this k node and we form the tool this is our I node Iki. So we find the k such that the distance Cik, this distance, is minimum, and we add this node. So our subtool now is Iki. Next we'll do the selection step. So given a subtool, find node k not in the subtool closest to any node in the subtool. Okay, so let's say, so now we find a node which is closest to any of these two nodes I and k. So here we can see that this node is the closest and it is closer to I. Let's say this is j. So now we'll add this j to our subtool. So the final subtool would be I, j, k, I. We inserted j in between I and k because in doing this increases the distance by the less amount as compared to if we have chosen any other node and inserted it between, say, k and I over here. So that's basically the nearest insertion heuristic. So the insertion step is determined like I said, find the arc ij in the sub2 which minimizes Cik plus Ckj minus Cij, insert k between I and j. So what this says is basically the same thing, like we have this Cik and then Cij and Cjk. So the new distances we are adding is Cij and Cjk, and the one we are cutting down is Cik. So we need to make sure that this Cij plus Cjk minus what we have reduced the distance, which is Cik, is minimum. Similarly, we can have the farthest insertion heuristic, which just is the opposite of nearest insertion. We do maximal instead of minimal. We add the farthest one. We don't need to go in depth, we just need to have a look at it. And also an arbitrary insertion, like between the minimum and the max, we can think of that arbitrary insertion as well. But all these are heuristics which don't give us the optimal solution. We just try to reach the optimal solution through these heuristics. So now we'll see another greedy heuristic, because one can think that let's start adding the edges in increasing order of weights. Like we can also do, like we order the edges in increasing order and keep on adding the edge with the minimum weight, such that we don't form a cycle in between. So we only form a cycle at the last edge when we have visited all the vertices. So let me show you what this means. So in this graph, these two nodes are the closest, so we add an edge between them, and we keep on doing the same thing for all the edges. And we can see that we are close to forming a tour, and we have made it. Yeah, so we can already see the problem with this tool. Like, see this cross over here. We obviously know that a better way would be to combine these two and these two rather than crossing over, because it obviously is covering more distance. So this also won't work. Also, there's a savings heuristic given by Clark Wright in 1964, and it's slightly involved, so we won't go into the detail because of the crunch of time. So we just skip this heuristic. So here we can see the performance of our heuristics. So the performance here is given in terms of mean distance to the optimum, like how much more distance, like let's say the optimum distance is some d, then how much more distance we are covering by our algorithm. So the savings heuristic covers 11% more distance. Multi-fragments, which was the greedy heuristic we discussed, has 12% distance to the optimum, and the nearest neighbor heuristics has 26% distance to the optimum. So we can see that this is not good at all. And this is the graph generated by our algorithms in a typical case where this is the optimal tour. This is our greedy tour. We can see these long edges. This is our nearest neighbor tool, and we can see how bad it feeds. There are so many long edges which are just wasting the distance. This is our savings tool, which is pretty close to the optimal tool. Now we'll try to improve our existing tool. We'll see how we can improve it. So consider this graph. What do you think, which local modification can improve this tool? What we should change? So as we already discussed, like we see over here that this cross is not at all good, and we can obviously change it by connecting these two and these two. So we'll do that exactly. we'll remove these two edges and rebuild another tour, which is equivalent to inverting a given sequence of markers. What this means is that, let's say we travel this in this direction, we went over here, and we travel this in this direction, and we came over here. So if we remove these two edges and we add this and this as the new edges, so what we will be doing is traveling like this and removing this marker, and this marker will remain the same. So we are actually inverting a given sequence of markers. If you don't understand that, simply take it that we are just removing those two edges and connecting by the other possibility we had, which is obviously good. Also, we can do something like, instead of removing two edges, we can remove three edges and try to rebuild another tour, and we can go on till any number, let's say 4 edges, 5 edges, k edges. So let's see how our two-opt strategy works. So our two-opt strategy is to select any two edges and then replace them with two other edges such that the Hamiltonian cycle is maintained and the total distance is reduced. So what we'll be doing here is actually greedy local search. Local search means that we are searching in our neighborhood, like we are currently having a Hamiltonian cycle, that's our current state, and we form another Hamiltonian cycle by replacing some edges, that's the new state, and these two states are neighbors of each other because we are just changing two edges. So that's what local search is. And greedy because we are always trying to minimize the distance, reduce the distance, so that's why it's greedy local search. So also we note that a finite sequence of two change can generate any tour, including the optimal tour. Here we say that a finite sequence of two change, we don't know how long this sequence can be. It may be as large as n factorial or something. So doing two changes doing a finite sequence of two change can generate the optimal tour, but we don't know the length of that sequence. So best what we can do is so what seems best to do is that we'll do this two change and until we get to the state with the minimum distance, that is the state that if we do any other two change, the distance will only be increased. So by this strategy we'll actually not be able to find the optimal tour, because let's say this is our answer after the two-opt strategy. So is this optimum? The answer is it's not, and we'll see why. So first let's see how well this two-opt and three-opt k-opt strategy works. So we can see the mean distance to the optimum. For two-opt it's 9%, three-opt it's 4%, and for some large k-opt it can be reduced to 1%. And the time complexity for the two-opt would be n cube, three-opt n4, and k-opt into the k+1. And the reason we didn't reach the optimal tour by doing our two opts greedily is because of the difference between local versus global optimum. So here we can see these on the x-axis are our potential solutions, that is the state space, and the y-axis tells us the cost. So let's say if we start from, let's say, over here, so if we start from, let's say, over here, and using the two-opt strategy we'll always minimize the cost, then we can go either over in this direction or in this direction. Let's say we started moving in this direction and we always minimize the cost, and we will eventually hit this point. Now at this point, this is the local minima. So any 2 opt would actually increase the distance, and since we are doing it greedily, we won't take that option. But the global optimum is this. So we can see that in order to reach that optimum, sometimes we have to take the actions which will increase the distance for a while, but eventually they will lead us to this optimum value. So that's why I said the sequence, the finite sequence which will lead us to the optimal value is not known, and it can be very large. So we can't just let go the algorithm to run forever. So we have to stop it somewhere. So greedy approach is one approach to stop it in finite time. And there are other local search heuristics like taboo search, which means that, to put it in simple terms, is that we take the steps which decrease the distance, and once we are at the local optimum, we allow some steps to be taken which increase the distance, and the number of those steps is predefined. Let's say some k steps, we define the value of k, let's say 10. So we'll allow 10 steps to be taken such that the distance is allowed to increase, because we need to pass these small hills over here. So let's say in 10 moves we can actually reach this hill, and after that we will actually be able to move closer to our optimum in this direction. And let's say it is possible that this value of 10 might be able to help us surpass these hills and reach us the global optimum. If the value of 10 doesn't work, we can increase the value of our k, which is the length of the taboo list. That will help us reach the optimum. So this is one heuristic. And also we can another thing in this is that when the search goes to a tour that is already seen, we restart with new tours, and we build new tours in a random way. There are also other meta heuristics like simulated annealing, genetic algorithms, variable neighborhood search. So in simulated annealing, local moves are randomly chosen, they are not greedily chosen. Neighbor acceptance depends on its quality. Acceptance process is more and more greedy. But we'll not go into the details of these heuristics, as I think the purpose of this video of getting to know the traveling salesman problem and finding the solutions, trying to find the exact solution, then trying to find the approximate solution using the heuristics, all this we have become familiar with now, and that was the actual goal of this video. So thank you for watching. Goodbye.